Hi folks, this video is to introduce you to vector quantities and scalar quantities. You've probably never even heard of these things before, but in physics class we are very interested in vector quantities and scalar quantities. So let's just get started. Let's just look at the definitions, and in and of themselves they're not going to mean much to you, but let's just read them and then we'll unpack what they mean. A vector quantity is a quantity with a magnitude and direction, while a scalar quantity is a quantity with only a magnitude. So what does this word magnitude mean? Because it shows up in both definitions. Well, magnitude simply means the amount or the number. So what is a vector? Okay. I'm going to first just talk about some examples of some things that are vector quantities, such as force, velocity, acceleration, displacement, and of course magnetic field and electric fields you don't know anything about. But let's just talk about force for a minute. Let's just talk about force. A force is a push or a pull. That's what a force is. So suppose there was a box on the floor and I wanted this box to move. I would come along and I would put a force to it. I'd push it. So I'd give it a force. Now the unit for force is called a Newton, and you really don't need to know that other than me just telling you that. But let's suppose I push this box with 110 newtons of force. The 110 newtons, that would be magnitude. And look which way this arrow is pointing that I drew. It's pointing to the right. So right would be the direction. Does that make sense? So to the right would be the direction. So like a force, for example, is what we call a vector quantity. Because think about it. Can you push or pull something without doing it in a certain direction? Think carefully about what I just said. Is it possible to push or pull an object without applying that push or pull in a certain direction? And the answer is no. If I'm going to push this box, I'm going to either have to push it to the left, to the right, up, down, in, out, whatever. I can't push something without doing it in a physical direction. So let's go back to this definition of a vector quantity. A vector quantity are quantities that have a physical direction associated with them. So direction, what direction means is like left, right, up, down, north, south, east, west, in, out. Okay, see, these are all physical directions you can point with your finger. When you're standing somewhere, you can say that way is up, that way is down, that way is left, that way is right, that way is east, north, south, west, whatever. Those are directions. So some quantities always have a physical direction associated with them. And the most obvious one is force. You can't push or pull something without it being in a certain direction. Now the magnitude is simply how hard you're pushing or pulling. It's the number, the amount of the force. But you can't have a force without a direction. You can't have force, the number for force. You can't have the number for force, 100 newtons or 110 newtons, without saying what direction that force is. So let's review this for a second. A vector is a quantity with a magnitude and direction. Magnitude is simply, I have it written right here, magnitude is simply the amount or the number. So in my example right down here, 110 newtons is the magnitude, and the direction is to the right. So let's take a look at some examples of vector quantities that you're going to see in physics class. For right now, magnetic fields and electric fields, it's nothing you need to worry about. I just put them on here just to be thorough. But force definitely has a magnitude and direction. And there's this quantity called velocity, which is basically, that's speed. But it's speed with a direction. It's accounting for which way you're moving. And there's acceleration, which is the rate at which speed is changing, and your displacement or your position. Your position also has a direction because it's always referenced from somewhere else. For today, for this unit in the summer work, I just really want to focus on these two things, force and velocity for now. Those are the only two vector quantities that we're really going to worry about for the sake of this summer assignment. Velocity is how fast you're going in a certain direction. You might want to write that down for yourself. Velocity is how fast you're going in a certain direction. Velocity is a vector quantity. Now, let's go back. I'm going to say it again. I'm sorry to be redundant in this video. What is a vector quantity? It's a quantity that has a magnitude, which means amount, and a physical direction, like up, down, left, right, and so on. Now let's contrast that with what a scalar quantity is. A scalar quantity is a quantity with only a magnitude, which means it only has an amount. It doesn't have a direction associated with it. And most numbers are scalar numbers that we deal with. Most quantities we deal with don't have a direction associated with them. So let me scroll down here. Let's talk about some scalar quantities, examples of scalar quantities. Like temperature. Temperature is a scalar quantity. While temperature can increase or decrease, you can have a hot day and say, boy, the temperature's going up. When you say temperature is going up, you don't mean up into the sky. You mean it's increasing. So temperature doesn't point left. It doesn't point right. It doesn't point down. It doesn't point west. It doesn't point east. It doesn't have a direction associated with it. Likewise, time. Think about time. 5 minutes. Does 5 minutes have a physical direction that you can point with your finger? No, it doesn't. It doesn't make sense. Like, time is just time. It doesn't have a physical direction. And speed is different than velocity. Velocity is how fast you're going in a certain direction. Speed is simply how fast you're going. It doesn't take into account your direction. Distance doesn't take into account direction. Mass doesn't take into account direction. Like in chemistry class, when you would worry about how many grams were in a particular experiment or something, grams doesn't have a direction. It's just the amount of matter in the object or in the chemical reaction or whatever it is. Grams does not have a physical direction. Mass is a scalar quantity because mass just doesn't have a physical direction. It doesn't. You don't say 5 grams up, down, left, right, whatever. It doesn't make sense to say that. And energy is also a scalar quantity, and you'll learn about energy later in the year. So I want to point out this distinction. Some other scalar quantities. Money. Money is a scalar quantity. Money doesn't have a physical direction. If I gave you $5 and said, what direction is the money pointing? That wouldn't make any sense. What else doesn't have physical direction? Think about your grade. Are quantities. They're mathematical quantities that describe your performance in a particular subject, but they don't have directions associated with them. You might say my grade is going up or my grade is going down, but your meaning of the word up and down isn't the meaning for physical direction. Your meaning there is increasing or decreasing. My grade has increased or decreased. So your grades also are scalar quantities. Okay, so let's review this one more time. I'm sorry to be redundant. I have to be because when I quiz students on this at the start of the school year, they still don't get it. What is a vector quantity? It is a quantity. What is a quantity? Quantity like force, velocity, displacement, acceleration. Those are quantities. The thing that you're measuring or computing is the quantity. So a vector quantity is a quantity that has a magnitude and direction. Magnitude means amount or the number, and direction is the physical direction you could point with your finger in space. Left, right, up, down, north, south, east, west, whatever. A scalar quantity is a quantity that has only a magnitude. It doesn't have a physical direction associated with it. And remember, magnitude is not a scary word. Magnitude simply means the amount or the number associated. with either the scalar or vector quantity. It's just the amount. Okay, so with vector quantities, we have to learn a little bit of new mathematics to deal with vector quantities. When we're dealing with vector quantities, we often represent them as arrows. And why do we do that? Well, let me give you a little example problem of why we care about direction. Suppose that there was a river, and we're looking down on a river, and on that river there was a boat. There's a boat on the river. So here's the boat. And this river, let's say that the river itself is flowing at a speed of 5 meters per second. And I drew my boat the wrong way. I'm going to draw my boat this way. And on this boat, somebody is trying to row across the river this way. And the person in the boat is rowing at 2 meters per second. So what we have going on here is the boat and the water both have their own velocities. Now, what is velocity again? It's speed with a direction. The river is moving 5 meters per second to the right. For the river, the magnitude is 5 meters per second, and the direction is to the right. See, vector, magnitude, direction. The magnitude's 5 meters per second, and the direction is to the right. For the boat, I'm going to call it up because the direction on your page would be up as you're looking at this on your screen. The boat has a vector velocity of 2 meters per second up. So it's going this way. So again, there's a magnitude of 2 meters per second, and the direction is this way. If I asked you what is the final speed of the boat, what would you do? Would you add 5 plus 2 and get 7? Well, since this is the first time you've seen this, if you said to do that, I wouldn't think that that would be an unreasonable guess. But that's not what you do. Think about this. If you were watching this, a person is trying to row the boat across the river while the river is moving to the right. Don't you agree that the boat is going to end up going in this direction? It's going to go diagonally. So that's what we have to figure out when we're dealing with vectors. We're going to be interested in how do vectors add together, and how do you take a vector apart. That's called resolution of vectors. We'll learn that shortly. We're concerned about this kind of stuff because the physical direction of these quantities matters a lot. So what you would end up doing in a situation like this is you would end up drawing these vectors. And the way you draw a vector is you draw a vector by using arrows. Arrows. Let me draw. Here's the origin. So for the river, we would say that the river has a velocity of 5 meters per second to the right. The length of this arrow, the distance from here to here, represents the magnitude. The longer the arrow, the bigger the magnitude. And of course, the direction is represented by which way the arrow points. So this is a really important piece of information that you need to know. We represent, when drawing vectors, we represent the magnitude. The magnitude is represented by the length of the arrow. Represented by the length of the arrow. So the longer the arrow, that means a bigger magnitude. And the shorter the arrow means a shorter magnitude. And what shows us the direction? Well, the way the arrow is pointing tells us the direction. So the direction of the arrow tells us direction. The length of the arrowhead tells us the magnitude. So that's the vector. This would be for the boat. That's the vector I would draw for the boat. Oh, excuse me, that's for the river. That would be for the river. Now for the boat has a velocity of 2 meters per second that way. Now I drew this arrow a little bit shorter than that arrow. Now, we're not going to do this to scale, which means we're not going to measure it You could do that, but we're not going to get into graph paper and all of that kind of stuff. We don't need to do that. We don't need to take measurements of the other arrows. It's just kind of subjective at this point. When a vector is large, you make the arrow long, meaning if it has a big magnitude, make the arrow long. If it has a small magnitude, you make the arrow length short. Okay, so let's go back to this scenario with the river. So this is our river. How would I determine the final velocity and direction of the boat? Because what I have to do is I have to add two velocities together to see what the final velocity of the boat is. So I have to add, somehow I have to add up this 5 meters per second that's going to the right to the 2 meters per second that's going up, across the top of your screen there. So I have to add that 5 plus 2, but I can't just add 5 plus 2 to get 7, because that does not take into account the directions. So when you add vectors, this is a big thing, folks. When adding vectors, you might want to write this down. When adding vectors, you always add vectors tail to head. What does that mean? Well, you see how we just drew these two vectors here? What I'm going to do is I'm going to put the tail of the boat vector at the head of the river vector. So let me show you what I mean by that. Here's the river vector. It was 5 meters per second to the right. And the boat vector was 2 meters per second this way. So do you see what I did is I put the tail of the boat vector. I put the tail of the boat vector at the head of the river vector. See right there? That's tail to head. I put the two vectors tail to head. And notice I didn't change their direction and I didn't change their magnitude. I left that alone. So I've put the two vectors together. Now, to get my answer, the answer is called the resultant. What I do is I draw a line from where I start to where I end up. This is called the resultant. That's my final answer, the resultant. Now, if you haven't noticed, we just made a right triangle. And because this is a right triangle, you see that the hypotenuse here is this thing called the resultant. And when you have a right triangle, you learned in your geometry class to use the Pythagorean theorem. So what I would do, the Pythagorean theorem is a squared plus b squared equals c squared. Well, in this case, the resultant is c. I'm going to call that r. Well, if I want to know what r is, look, r is just the square root of a squared plus b squared. So if I wanted to know what the resultant was, all I'd have to do is I would do 5 squared plus 2 squared. What's that end up being? That ends up being 25 plus 4, which is a square root of 29. See, this would be 25 plus 4, which is the square root of 29, which if you punch that in your calculator, that ends up being 5.39. And the unit on that would be meters per second, because that's your unit that we were dealing with. We're dealing with velocity vectors. So this resultant is 5.39 meters per second. So what you would see is, let's go back to this picture with the boat. What you would see is you wouldn't see the boat going to the right at 5, and you wouldn't be seeing it going up at 2. What you would end up seeing is the boat going this way at 5.39 meters per second. That would be the actual observed velocity of the boat. Now, to make this official, the last thing I would have to do is I'd have to figure out what theta is here. There's an angle associated with it, and I'd want to know that angle so that I could accurately describe the direction. And I could figure out that angle quite easily because I could use inverse tangent. This is why we did the trig functions. We looked at the trig functions. Inverse tangent is going to give me the angle. So opposite over adjacent. My opposite side is 2, and my adjacent side is 5. If I take the inverse tangent of 2 divided by 5, I get 21.8 degrees. So that angle would be 21.8 degrees. So on my picture here, let's go back to the river. This would be 21.8 degrees. So look at that. I have my magnitude, and I have my arrow pointing at an angle of 21.8 degrees oblique to the parallel of the river. And that would be the final velocity of the boat. Now, this thing called the resultant, right here, I called that the resultant. The resultant is your final answer when you're adding vectors together. When you add vectors together, the resultant, it's called the resultant. It's the sum of 2 or more vectors. The sum of 2 or more vectors added together. My pen's not working here. There we go. So that's what's meant by resultant. So, okay, just from this little sample that I did for you, I don't expect you to be able to add vectors perfectly right now. I'm just trying to give you the big picture here. Do you see when you're adding vector quantities, what is a vector quantity? It's a quantity that has an amount, magnitude is what that means, and it has a physical direction. You can't just add vectors together by just adding magnitudes. You have to take into account the direction. So how do we add vectors together? What you do is you draw pictures of the vectors. How do we draw pictures of the vectors? We use arrows to represent vector quantities. The length of the arrow represents the magnitude, and the direction of the arrow obviously represents the direction. So a short arrow is a vector quantity with a big magnitude. A small arrow is a vector quantity with a small magnitude. And obviously the directions are the directions. Now once I have those vectors drawn, what I want to do is I want to move them and redraw them tail to head. And the order doesn't matter. It doesn't matter which tail goes to which head. But you want to put them tail to head, not tail to tail, not head to head. Tail to head. So the head of one arrow should be touching the tail of the second arrow. So you always add vectors tail to head. Do not forget that phrase. Vectors are always added tail to head. Say it out loud. Vectors are added tail to head. Then what you do is you do the necessary geometry. Typically use the Pythagorean theorem to figure out the resultant. That's whenever the vectors are added at 90 degrees. That's normally what you do. A squared plus b squared equals c squared. And you also want to calculate the angle, because you need to know which way the vector points, and you often have to report the angle with that. The thing called the resultant is the sum of 2 or more vectors. Now, I have some pet peeves when people are working with vectors that we need to talk about. When you draw vectors, when you're drawing a vector, a lot of times I see students, they'll just draw a line like this. You have to have an arrowhead whenever you draw a vector. It has to have an arrowhead because that signifies the direction. And you also, if you're given information about angle, you want to make sure that you include that angle, whatever it might be. So suppose I told you that we had a vector, we had a velocity vector. Let's suppose velocity was 30 meters per second, 26 degrees north of west. What does that even mean? How would you draw that? Well, you have to think like this. You have a origin that you're going to start at. Well, this would be north, east, south, west. So it says 26 degrees north of the west axis, north of west. The west axis is over here. So I'm going to start there and I'm going to go 26 degrees to the north. So that means I'm going to draw a vector like this. And this angle in here would be 26 degrees. and the magnitude would be 30 meters per second. So the length of this arrow represents 30 meters per second, and there's my angle, 26 degrees. This is a properly drawn vector. It has an arrowhead and the angle is referenced. What if it was 26 degrees north of east? Well, if it was 26 degrees north of east, here's what I would do. I'd go this way. It would be 26 degrees north of the east axis. So this would be 30 meters per second, 26 degrees north of east. What if it was east of north? Ooh, what would that be? Well, that means you'd go 26 degrees east of the north axis. So we'd go this way. And this angle in here would be 26 degrees. We'd be going 26 degrees to the east of north. What if it was west of south? Well, we'd go this way. This would be 26 degrees. And this would be labeled 30 meters per second. See, the magnitude is 30 meters per second. The 26 degrees is helping you identify the direction. So this is your big introduction to vectors. I would like you to work on vector worksheet number 1. I believe I've set you up pretty well to be able to answer all of the questions on vector worksheet number 1. When you're adding and subtracting vector quantities, remember, you can't simply add or subtract the magnitudes because you have to take into account the direction. That's really important. Scalar quantities, you can just add and subtract and it's totally fine, just like normal, just like you would do with anything else. But with vector quantities, we have to take into account the direction. All right, I'll see you in the next video.